Okay, well, again, welcome to everyone. I think you know me as Bob Hoyt, and that's Dave Petrishkoff as my partner in crime here and colleague. I want to ask, though, I think, Dan, you're a new member, and any others that join, please unmute and tell us a little bit more about yourself.
Hey, everybody. Good morning, and thanks for letting me jump in here. My name is Dan LaRiviere. I'm a neurologist at the Inova Health Center in Northern Virginia. I just got through taking the AI class offered through the ABAIM, and through that class learned about this deal. And so I wanted to just jump in and kind of see what it's about.
Okay, well, I hope you get something out of it. Did I see that you're an MD-JD?
That's correct.
Okay, well, that's a first. So it's nice to have you on board, and there are legal implications of a lot of what we're talking about, particularly as we talk about ChatGPT and related issues. So again, welcome. Who else is new today? Anybody?
Good morning, everyone. My name is Jawahar. I'm a NICU faculty at UT Southwestern Medical Center, and I'm also finishing my master's in biomedical informatics in AI track. I'm learned about the workshop at AI Med conference, and this is the first time I'm joining here. So interested in learning more.
Okay, well, it's nice to have you. Obviously, you're going to have some interesting background, and we're going to discuss AI. We can't dwell on it too long because we have a lot of basic data science to cover first, which is really important. So that being said, I think I'll go ahead and share screen. I'm still admitting people. Let me see. Now, I'm not sure share screen. I guess I've already.
Yeah, we can see your desktop.
Okay, there's left something says end meeting for all, but anyway, I'll ignore that. Okay, so in terms of homework, let me, I'll post the homework in a second here. So this is last month's homework, basically, and I need to move all the screens out of the way, but the idea behind this was to use the Framingham Heart data set that is located in the Chapter 4 folder, which we've showed you a little bit about the file share in a minute. With the new people that are on board don't know that we have a file share site. But this is a data set that 15% of the people went on in 10 years to develop heart disease, 85% did not. And so when you open the file menu, you want to be sure that you set the 10-year heart disease as target, and anytime you change it, you hit apply. But for the new people, it gives you a chance. You can actually, if there's a mistake, and so far I've never seen it, if something is labeled numerical but needs to be categorical, you can change it. You can also make anything a target if you want to for a model. Tells you the features, whether you have any missing data. It also gives you more options. Again, a lot of what I'm seeing here is blocked by Zoom icons, but you can actually pull data from a URL, such as a Google Sheet. That's, Google Sheets have URLs, or you can upload over here. You can upload your own data, and there's a few default data sets. The ones in black are ones that come with the file menu that you can use. So the file, basically, the file icon, or excuse me, file widget is where you often start. Now I put in here what two methods or widgets, there's really three, not shown, tell you whether the target class are similar in number. In other words, how would you know what percent had heart disease and what percent did not. Anybody can chime in if they want to, but I've gone ahead and so the answer is you could look at a distribution and see that the people without heart disease were far greater, or you could use feature statistics and get that same qualitative idea. Are they matched? But best of all, to me, the right answer is the box plot, where in the upper you put 10-year heart disease and the lower 10-year coronary disease. Now you see the actual numbers. Blue means no heart disease. So there's 3,500 versus 644. So to me, it's a good starting point as you start to explore data to be sure you don't have class imbalance where you have way more people with, let's say, the absence of the condition you're interested in than the people that have the condition. So that is just on your list when you try to look at data, clean up data, understand your data. And the easiest way in orange is the box plot. And I'll demonstrate that more in just a minute. So we connected all the algorithms, to the test and score widget. We're going to look, this is just training data. The exercise homework data is going to look at train and test. And that'll attach as soon as I get a chance. But so here's the results of doing the classification model to determine who developed a heart disease at 10 years. You have to set the target to 1. Here's your performance. And something should catch your attention immediately. As specific or specificity really looks good, maybe too good to be true. AUC is not as good. Accuracy is very good. But when you look at recall, which is sensitivity, it's horrible. Precision's poor, and the F1 score, which is the harmonic mean of precision and recall, is also poor. This should alert you of a class imbalance. That should be your first inclination as you're dealing with a class imbalance. And we're going to be discussing that today. So that's why I chose this, because that sort of should let you know that this is something you should be looking for. And let me go back to this for a second. The constant widget really looks at frequency. I mentioned that there are about 85% people without heart disease. Looks like the accuracy of 85. That came from frequency only. So this, a constant is a way of looking at your baseline. It's just saying, I think there's an 85% chance it's going to be no heart disease. So this serves as a baseline. You always have to do better than the baseline. That was the point of adding the constant widget. So we'll be going over more stuff in just a minute. So let me see what I have next. The article I sent most people, and let me pull up. I can, again, need to move all my Zoom icons. This one was one I sent, came from the New England Journal, August the 3rd, talking about 20th century Pandora's box. And I can't take enough time right now to go over it in detail. But in essence, what it says is introducing artificial intelligence, particularly what you've seen recently with generative AI, has opened Pandora's box. It's going to change medical education, probably partly for the better and conceivably for the worse, for reasons they explain. So their appeal to you is get on the bandwagon. So basically, industry doesn't tell you what to do. You tell industry what to do. You must be knowledgeable about large language models, the good, the bad, and the ugly. That's pretty much summarize this perspective. And I can try to put this one back in the chat as well, because we have some new people, so everybody has that. The second article that came in after I sent that out, it came out Monday in JAMA, and let me increase that, was by the head guy. head data scientist at Stanford, Dr. Shah. And it's on the creation and adoption of large language models in medicine. And basically, he like everybody's talking about the tremendous potential of it. But the point is, we need to help design how they're trained as an example, but get involved. So just read this statement: applications powered by large language models are increasingly used to perform medical tasks without the underlying language models being trained on medical records and without verifying their purported benefit in performing those tasks. So again, we need to be part of the team that evaluates and helps for training. That's the point of the two articles. All right, I'm going to pull up, let me find it here. That's not it. What I may have to do, let me look at recent. There we go. This is a data set, by the way, that came from Kaggle, and it actually came from Glassdoor recruiting. And I thought it was interesting about data science salaries, but it gives you an opportunity to once again use the box plot real quickly. So, and this will be an exercise in chapter 2, which you've already had, but we've added this as a practical exercise. So just as an example, when you go in and look at location here, you notice that almost all are United States. So that maybe said, I think I'm only going to mine the United States. When I looked at the year, I noticed that almost all are to 2023. So for simplicity's sake, I'm mining only 2023. And when I looked at employment type, so again, I'm clicking on the same thing in both. And the answer was almost everybody was requesting full-time. So then I said, well, I'm going to go ahead and filter it. And what the way to do that is to use the select rows, where I put employment type as full-time, year is 2023, company location is United States, just to keep it short and simple, because when I go back to the file menu, for instance, salaries, I use salaries in US dollars only. I did not, there's some things I skipped, like salary in other currency and whatnot, I was not interested in. So I basically, that's a way to hide it, if you will. So doing that, now I have information. I can mine it, and I don't want to spend too much time in this, but I want to show you how easy it is to say, take job title. The problem here, by the way, is interesting. There are 87 job titles, too many to mine. So I took the 4 most common, and in orange, you can do something cool. In a Mac, you just hold down the command key, click just these 4, and when you highlight it, you can then send it forward to either a data table or to another box plot. So now, instead of looking at 87 categories, which would be unyieldy, you select salary in US dollars and job title here, and you can compare them. Note, though, the huge standard deviation. So this is just an approximate mean, or it is the mean salary, but it's plus or minus a whole lot. And I'm going to skip over some of the other findings, but just say, again, it's so easy to go in and just start looking at various things. You can, again, do all kinds of cool stuff. Salary by company size, so forth and so on. But we don't have time today to go over that. But that is in the file share site, which I will demonstrate in a minute. And actually, let me just do that now. Many of you all have not seen, because you're new, have not seen our our website rather, no code data science. And basically is a file share. So if we're discussing chapter 2, for instance, and the exercise is on the latest data salary, that's where you'll find it and can download it just for convenience. All right, while I'm there, I wanted to comment that Dave and I have been playing with using large language models for data analysis. And I've used several. The criteria is it has to accept decent sized files, and it has to also generate code. Claude and Claude Instant will accept a file of 100,000 tokens, which is about 75,000 words. Claude Instant is a little smaller and faster than Claude 2. I don't need to bore you with those details. There's 500 large language models out there. But just to get you to understand, we're running all kinds of data science experiments trying to see how good it is. So far, it's only made one mistake, and that was giving us a confusion matrix based on too few of patients. When I said you made a mistake, it said, I'm so sorry, and I'll correct it. And it did. Did somebody want to make a comment? I did want to tell you another thing, that this is hosted on Poe, which aggregates all these other large language models. What I can't tell you is the exact pricing. At this point, what I'm doing is free using Claude Instant, but I think at some point it won't be. You can also create your own bot. So just remember Poe is an interesting option, and we'll be talking more about using AI for data analysis. But the other take-home point is you need to know data science, some basic stats and whatnot in order to perform data analysis using an AI large language model. As a newbie, that just simply won't work. You won't know when the results are correct or incorrect. So it's really important to have a background in this workshop or however you do it, so you can intelligently use AI to do data analysis. So with that, we'll be going over that more down the road, I'm sure. I want to remind you the next workshop is September 9th. With that, I'm going to stop sharing and turn it back to Dave. And I'll try to post what I talked about in the chat.
Okay, just a second here. All right, Bob, let me know if you're seeing the screen now.
I'm seeing a frozen image of you. I'm not seeing your screen.
Okay. It says
I
you're
can see
sharing.
it.
You can see it
We can see your screen, yes.
with the Word document?
Yes.
Okay, good. All right.
Hey, I'm not. Let me try to escape that. Okay, now I am.
Okay. So I'm going to first talk about a few announcements, and then I'll roll right into some of the materials out of the book that we're going to talk about, and then Bob and I will go back and forth on that. The first thing I wanted to let you know, we mentioned this before. Now that Bob and I have this book completed, we're still going back and each chapter trying to do some more final editing, but the book is complete now. What we want to do is approach various associations and try to get continuing education units for that when we train this, so that, you know, there are those people that have certain types of jobs where that they are actually required to have a certain amount of continuing education points and units for their continued whatever participation in association or elsewhere. So these are just some of the associations we're targeting. If any of you have any other ideas, please email that to us. And so, yeah, we're pursuing that. And also, we've talked about this before, and since our last workshop, Bob and I went through now, and we have every chapter, subchapter, subchapter, we have everything labeled as a 1, 2, or 3 star. And what does that mean? Well, the 1 star is, it's kind of like, oh, it's easy reading material. It's for a beginner. And the 2 star is for intermediate readers, and obviously the 3 star is more for advanced readers. So we have that laid out. And we're going to use that also, that 1, 2, and 3 star, as a basis for the 3 levels of certification that we plan on offering for training. What we've also started is conversations with universities, and we've started out slow, but we plan on picking it up quite a bit. We have already for this month, we got a pretty serious conversation with the university that is willing to entertain our classes, our seminars, and being able to have that certified then under their university logo as a certificate, probably a joint certificate between us and them. So, because there are certain people that like to have, you know, certificates for certain advanced topics that come through a university. So we're having those conversations. And so if any of you happen to know certain people that are the heads of continuing education at certain universities that you wouldn't mind introducing us to, that would be great. We know quite a few ourselves, but if you have a recommendation for us, we'd be glad to look at that and follow up on that. So as far as the star ratings are concerned, what I'm going to do now is just kind of skim through. You can see, like in chapter 1 in the table of contents of our book, you know, all these stars, they show up not only throughout the book where they're there, but also in the table of contents. So you can see, obviously, chapter 1 is all pretty much 1 star. You get into like chapter 4, I skipped ahead, you could see right away at the top, we'll talk about, all right, chapter 4 is a mix of 2 and 3 star topics. And then you can see individually what each of the chapters and subchapters, how they're labeled. And then you can see like something, I'm jumping way ahead to chapter 11, which we haven't reviewed in this workshop yet. Text mining, that topic actually has, you know, 1, 2, and 3 star content. And chapter 12, which talked about, you know, integrating continuous improvement techniques with data science and industry 4.0, that's also a 1, 2, and 3 star. So we've gone through and labeled that, and now what we're going to do later is, as I said, we're going to then lay out the body of knowledge for each of those 1, 2, and 3 star certification levels, and take that from there. So before I jump into the training material from the book, I did want to make an announcement. Bob and I were discussing this in the past few weeks, that, you know, it's always great to have these Zoom sessions, these workshops, but very often, as Bob and I talk in a monologue, we certainly encourage dialogue and participation in the chat and everything, but we also want to do a general invitation that if any of you feel that you would like to have a personal conversation with Bob and I on a variety of different topics related to this book, feel free. And not only feel free, but we definitely would love to have you set up a Zoom call with the two of us, just to talk, because very often there's interesting conversations that can be had between, you know, very small groups of people that are somehow, you know, sometimes overlooked when we have a large group like this. So we want to make that available for you. So if you'd like to take part in that, please send us an email with some dates and times that work for you, and then we'll try to set up that type of a call. So what I'd like to do now is we'll now hop into the materials from our book, and we left off in chapter 4.5 where we're talking about JASP models. So again, what are JASP models? We have Orange, which is all based on Python, and then we have JASP, which we've also included in our book for a variety of different reasons, but JASP is based on R. And JASP is probably the simplest to use piece of software, analytical software that I've ever seen. It's basically, you tell it what you have to tell it, or here's my target variable, here's my predictor variables. And then you just basically uncheck or check in what you want in JASP, and then it'll create that for you. And I'll show you some examples for sure in a second here as I move on. But there's also, when you get into JASP, there's also these 4 little icons that are available, and I'll explain what they are. The one on the far left is you could edit the name of the section you're in. You could duplicate it, because those are the top 2 on the left, and then you have the blue eye, which is very important, and I'll demo that when I open up a JASP file. And that's very good, informative information, background information on that section you were in. And then the X says you want to get rid of that section that you've just opened. And I'll demo that in a second. So let's first of all talk about linear regression. So linear regression is a very powerful type of topic. It's available through just normal statistics, or also through a machine learning mode where it'll partition your data and training and testing data. So it's a very good method, very standard method. And one of the more modern versions of a linear regression is what is referred to as regularized linear regression. And what that does, and I'll show you where that is in a second also, it's under the machine learning module in JASP, and that allows, and the regularized linear regression, what that'll do is it'll automatically compensate for certain types of overfitting and underfitting and multicollinearity. And let me go into JASP at this very moment and show you what that looks like. And I'm going to pull over a JASP file. Somebody let me know if you could see this file, just to make sure that. Okay, good. So here we are in JASP now. And then I first of all talked about linear regression. So how do I first of all find that in JASP? Well, I go under regression at the top, and I happen to say, yeah, I want to have linear regression. I have other options, but I use that. And then this section opens up, and then in the linear regression, and in this case, I have a body fat data set where that's a % body fat for a bunch of individuals. And then we have also the covariates, which are the predictor variables, and they are put here. They used to be over in the far left, and I just right arrow them over to where they belong, the covariates or the predictor variables. And then I go down over here under each of these areas under, for example, stats, and I just check or uncheck what I want. And then that will automatically appear on the right. And you can see I checked as an example here, collinearity diagnostics. And if I want to have an expanded view of the right, then I just do this arrow, so I maximize this. So now it's showing me all the boxes that I checked on the right with all the analysis results. And sometimes I have to scroll a little bit to the right to see all these larger tables that are there. Or I could go under here and do, control minus to minimize that and make it smaller so I could see it. And you can see over here, it's showing me all my VIFs, which is a measure of multicollinearity, and anything else that I happen to have checked in that section. So when you go down into, for example, I also said that another version of linear regression is regularized, right? So to get that, I have to go under the machine learning section. And under the machine learning section, I have all kinds of options. And what I did is I checked the regularized regression option. And let me show you what that looks like. Here I got regularized regression. And again, I said my target is body fat. I have then all my predictor variables, which are various measurements and circumferences of, the hip, the thigh, the chest, the neck, and so on, all in centimeters. And then again, I'm just checking what I want or unchecking, and then it'll automatically offer that on the far right side. So this is really nice. This is machine learning. This is, I'm telling it over here that I want to have 20% of the data being used for holdback data. And you see a bunch of variety of other things that I had checked. And I also said I want, it was checked here, is I want to have the predictive performance. And also down at the bottom, I have my choice of algorithms. So under the regularization, you can see if I look at this down arrow, I can see I have a choice of lasso, ridge, and elastic net. And those are just three different methods of lasso is the most toughest one on multicollinearity. Depending on how you set the lambda value, it'll knock out a lot of the multicollinearity. And also, you can see I can switch to ridge or elastic net. Elastic net is a blend between lasso and ridge. Now, what's interesting is you could see I have this option here. I could do the same analysis in orange, but JASP has a very unique feature where that, you can see right now, I'm circling it. The optimize section is highlighted, which means I've now selected lasso and it's optimized. So it's going to automatically select the best regularization level that will give me the lowest level of error in the model. And you can see over here, the one I'm circling right now, the vertical axis is the error. And you can see in this case, and this is the lambda value, which is called a lambda for regularization level in JASP. It's called alpha in orange because orange uses Python, and a lot of these symbols, sometimes they're used for something else in these programming languages. So a lambda here is alpha in orange. But as you can see here, I have the lowest error by it's automatically picking this regularization or lambda value almost zero. So it automatically picked that because I said optimized. And you can see, just let's have a look here that under, I have an R-squared value of 0.657, right? And if I click on ridge, it will then, the wheels will spin a little bit and it'll automatically go through a recalculation phase and recalculate that same thing for a different type of algorithm. And you can see the spinning is still going on. And then it'll not only update the R-squared value, but it'll update the predictive performance value over here. And this is a very important graphic right here. This tells you what are my observed values, that's the real data, and then the predicted values for the actual observed. And when you see too much of a deviation from the line, which is a perfect fit, compared to the dots, then you know you're a little bit off. And here I got a 72% R-squared with lasso. And let me go back in with ridge, I'm sorry. Then I go back into lasso. And then if you carefully notice, everything will get recalculated and the charts will get redrawn to show you what's going on. So that's a really nice feature. And like I said, it's automatically picking the best regularization level. So that's a nice feature. Now, as an example in orange, and I'm now pulling over an orange screen. Somebody let me know if they can see the orange screen.
Yes.
Okay. So here I did the same thing with linear regression, but here I have the file, the body fat data. It goes into my test and score over here. And here I get, when I double click on that, I have to pull that over to this screen. I can see the scorecard of what's the R squared there. But here when I click on the linear regression tab in orange, you can see here it says alpha. And alpha is the same as lambda in JASP. And I could grab this and shift it back and forth. And so in orange, I got to do a little trial and error to find out what's going to give me my best R squared and what's going to give me my lowest error value. That's a little trial and error. So that's the really nice thing about JASP is it'll automatically cycle through all these different levels for a lambda or alpha here in orange and tell you which ones are the best ones. So if I'm starting out and let's say if for whatever reason I want to really stick with orange, then I would say, okay, instead of experimenting with high, low, and mid levels for regularization in orange, I could take the tip that I got from JASP that is telling me, hey, Dave, you're going to have your lowest error values if you stick with pretty low regularization levels. So that's a good tip. And that's also how you could go back and forth between these pretty valuable software programs that are pretty easy to use. So now I'm back into the MS Word document where I'm showing you where we talk about linear regression, and we mentioned some of the things that I've already shown you, and there's a lot of things that you could check and uncheck and do in JASP and have it calculate some very good analysis for you. So we like to bounce back and forth between orange and JASP, but depending on which of those techniques are either, for starters, do a really good job for us for one reason or the other. In this case, JASP, it'll do automatically optimizing the regularization level. That's a nice feature. And then we'll go back and forth as required between the two. Now, logistic regression, and again here, this is a section talking about what JASP can do. It's very similar to what I showed you in the linear regression, but here we have VIFs. And let's talk about VIFs as an example, which is a measure of multicollinearity. And that's another reason why we go back and forth here to JASP, because JASP calculates the VIFs and orange does not. So if I want to know which VIFs are above 5, which is a level of, multicollinearity that's pretty high and going to cause some issues, I can only find that out in JASP, and then I go back in orange and I use that guidance for that. So when I'm in logistic regression, let me pull a model over here of a heart disease model from JASP onto the screen, and let me know if you could see that.
Yes.
So here we got logistic regression. What do I have to do in logistic regression? I tell it, okay, what's my target variable, which it calls a dependent. So I just right click it over here. What are my, continuous variables on? I'm going to put them under covariates, and which ones are categorical that I toss into factors. And the same story, I just check or uncheck anything that I want over here. And then if I wait a little bit, it'll then calculate them on the right. And you can see here I have also multicollinearity diagnostics, that's checked. So I got a table over here of all the VIFs. And then I have all the other values and everything else that I want. So that's how I do the logistic regression in JASP. Pretty simple, check and uncheck. And this is again showing just an example from our book on this table here of you can get the p-values and a lot of other stats for a lot of the predictive for the X's that you're putting in there. Then also in JASP, I could go under machine learning algorithms, and I have a big selection there too. I have a big selection in orange, but I also have a selection in JASP, and bear with me, I'm going to pull one over to show it for you, and hopefully you can see that right now. And for example, when I go under the machine learning section, you can see I have whether I got a regression or I have classification or clustering. I can see all my machine learning algorithms that are available for me, and I could click on those and use them. Now, the disadvantage of JASP, and it's really tied to some of the disadvantages that R has, is I can't test multiple algorithms at the same time and then let the test and score widget that I have in Orange tell me which of the algorithms is the best. I have to test them one at a time. So you can see any one of these algorithms here. Let's say if I have a classification model, I got to do every one of these algorithms individually. I got to save their scorecards, and then I got to compare them against each other. So that's a little bit annoying. Where that, I get it's a very rapid process. In Orange, I could, go up to, 10, 11, or if I want to do derivatives or options of different algorithms, I could go all the way up to 23 and more of them. And it'll then compare them, as many as I want to. And it'll tell me which one is the best when I click on, let's say classification accuracy is my most important metric. I click on that from high to low, and then it'll show me which model is best high to low. So that's, one of the pros that we have in Orange compared to JASP. So you have to know back and forth. All right, in JASP, I have some nice things like I could get the calculations for VIFs, which I don't have in Orange. So I go a little bit back and forth between these models using the features that they have available. And then this is just showing you a lot of the evaluation metrics that are available when I do predictive modeling and their machine learning and JASP. So it's got a very nice, robust list of long metrics it's looking at. And then again, we just list here the different algorithms that I already showed you that are on the list in JASP that are available. And it also has an automatic feature for, you can see here like the decision trees. Not only will you get a decision tree, but it automatically throws in what is referred to as a feature importance table. Now in Orange, it's called something different. It's called a rank feature. Does the same thing, just looks a little bit different. And then also automatically the random forest algorithm in JASP will automatically also toss in the feature importance graphic without you having to check something to say, I want to have it. And those are also always very important. And you can see here, this is just, it's similar to like a rank widget that we would get output from Orange, yet it's a little bit different. I don't have the little lines of the Paretos, but it is ranked from highest to lowest based on its importance value that it assigns based on a number. So very similar. So what I'm going to do now is hand it back to Bob, and he's going to talk about ML ops. So I'm going to stop sharing, and Bob, hand it back to you.
Okay. And before I get started, Sarah, do you want to unmute and tell us who you are and where you're from and what your role in life is currently?
Hi, my name is Sarah. I am a medical doctor from Pakistan. Currently, I'm working as a clinical informatist here in Arizona, and I work at Common Spirit Health. So I'm interested in machine learning and AI. I know that I have taken a few classes, I think one class with you before. So I just wanted to be on your list and, get acquainted with everyone. Do this, learn this.
Okay. Well,
Thank you for having me.
Sure. It's nice to have you again in a class together. So, all right, I'm going to talk about ML ops very briefly. It's a term you see from time to time, particularly when you talk about specifically machine learning, where there are three phases, if you will. I'll scroll down where they divide this into experiment, develop, and operate. And it's really telling you, you start collecting the data, you develop a model, and then you operate that model, and then you have long-term monitoring of that model. We'll talk about how models can go wrong with model drift and concept drift. But the point is that this whole process, and notice they're all integrated, they're all circular. And now you have data engineers and ML op engineers that help create pipelines and make this whole process happen. Large organizations tend to hire the engineer before they hire the data scientist to get all this set up so it works from the beginning of data acquisition to actually operationalizing the model. So all those steps have to be considered, but I just wanted to, again, remind you what ML ops mean. And with that, I'll turn it back to Dave.
Okay, bear with me. Let me share my screen here. Okay, let me know when you can see the MS Word document.
We can see it.
Okay, good. So now we have a section here where we talk about tackling model challenges. There's a lot of model challenges, and it's a very interesting comment. Those of you that have studied statistics have heard about George Box made a very famous quotation that's used over and over again. He said, all models are wrong, but some are useful. And I added in the words in there where when he says all models are wrong, what he really meant is that they're not perfect, you know. And when he talks about models, what is he talking about? We're talking about statistical or predictive models. So that's always very important to understand, to ground us, because a lot of people say, yeah, wow, okay, I just did a predictive model. Okay, let's run to the bank and use that, and I'm going to use that to predict you know, the lottery and to predict everything under the sun and, you know, diseases and everything. You know, anybody can create a model, but to tune that model to make it improved and better, that takes a lot of tuning and a lot of experience and a lot of hard work. So it's always important to understand that this quote from George Box is very pertinent. So whenever you do a model, don't just slap yourself on the back and say, I'm done, I did a model, let's start making predictions. Keep in mind that those models are not perfect. And depending on how imperfect it is, it might actually be in the category of useless. So keep that in mind. Anybody can make models. Not many can make very high accuracy models after all the tuning that's required. And if you look in the literature, you're going to find also that about 80% of the predictive models don't even make it into what we use the word production, which means they don't get deployed by that company as far as internal or customer facing external models. Now, why is that the case? Well, you know, a lot of people like to blame leadership and say we have inadequate leadership in our company, and that's why our models just don't make it there. Well, you can't blame everything on leadership. You know, a lot of times, you know, leaders might get totally excited and they might let, you know, a data science team let them loose on a certain topic without fully understanding what's possible and what's not possible. So a lot of times that happens. And then when the data science team looks at what data is actually available, they might say, hey, you know what? All right, sure, we'll do a preliminary model, but we can't really deploy this. So a lot of it is a lot of because of the back and forth between the data science team and management, of management saying we want this, and the data science team might say we can't quite pull that off, or maybe the data science team, they do the best they can with the data they have, and it turns out that the model is just not accurate enough to launch in production, because it's just not either accurate enough or not generalizable enough to a population that has not been seen yet. You could have a situation where that your model looks great, your model performance metrics look pretty good, you're happy. And then all of a sudden you expand the data that you have the model look at that it hasn't seen before, then all of a sudden your model performance metrics drop like crazy. And when that happens, we say the model is not generalizable, which means, well, which means that it worked great on the data set that you had, but when we start to look at data that it hasn't seen yet, it's really not doing a great job. And how does that happen? Well, you might be looking, originally at a very specific cherry-picked group of patients, and then all of a sudden, when the reality hits you that there's, the other patients that you really want to predict for have a very wider range of demographics and all kinds of other different mixes, that all of a sudden your model, it just does not do very well at all, and you cannot productionize it. So that then becomes one of the models that gets thrown in the hopper, the delete file, so to say, that, hey, we're not going to put it in production. That's one of the 80% that didn't make it to deployment. So so those are things that you really have to watch out for, and we'll talk a little bit more about that. And then there's another thing that we have to look at is once you put something in production, you have to keep an eye on that model to make sure that you don't have model drift. Now, what in the world is model drift? Well, part of it I already explained, that it worked great with the data I had, and all of a sudden, when I'm starting to say, hey, model, I start to predict, I have 50 new patients a day, start predicting them, and then all of a sudden you see that what correlated before is not correlating. And what model performance you had before is really quite a bit lower. And we call those drift concepts, we call them concept drift and also data drift. The larger term is, first of all, called data drift. So if your model the numbers are they're looking quite a bit different of let's say the values of blood pressure or any type of lab value for a patient, they just look different than what you train the model on. So that would be referred to as data drift. And concept drift is a situation where that, we might have had a correlation between one of the lab values and one of the diseases we're tracking, but all of a sudden in the new data that we have, for whatever reason, that correlation is not there anymore. And that, again, could be for a lot of different reasons. It might be that you have different patients that have different comorbidity levels, and certain things that correlated before on a certain subset of patients, they don't correlate again on this with the new data, and we call that concept drift. So we always have to keep an eye on these two concepts, because if your data results are drifting, and if your data itself, the underlying values you're collecting on lab results and whatever are drifting, it can really do a bad number on your performance values for your predictive model and mess it up. So what do you do then? Well, that's where we then have to use the concept, what's called retraining the model. You say, what in the world is that? Well, now that your model has been exposed to all kinds of new data it hasn't seen before, and some of the correlations are out of whack and that type of thing, well, you might want to now include that new data into your whole model building process, which you start over from scratch, basically, because you can't assume any assumptions are correct anymore, and you retrain the model. So it's really a kind word for saying you're back to the drawing board of rerunning the models, rerunning all your algorithms. And what was your favorite algorithm before might be, not your favorite model. It could potentially be one of the worst models. You just don't know. So when the numbers start to change, the performance of your model starts to drop, you need to retrain the model and go through the same process you did before. You get new data that comes in, you have to make sure it's wrangled and it's correct, and and all that kind of thing. And if you have then, missing data, you got to impute that and so on and so forth. And you got to basically start the whole modeling process over again. We call that retraining the model. So again, when do you retrain a model? Well, when your values that you've inputted have now drifted to the point where they're quite a bit different, or maybe even statistically significantly different than the data you had before. So that's that concept, and we talk about that a little bit more in later chapters. Then we get into other, there's other types of model challenges. Again, this whole section is about model challenges. So now we got model bias and fairness. You say, well, what in the world is that? So, we talked about earlier about bias variance trade-off, and what we're trying to do there in that concept is balance, overfitting with underfitting to have the right type of balance. So that's kind of like a trade-off. But there's a lot of these different types of trade-offs that we have to deal with that could really affect our model and the fairness of the model. Let's say, for example, on a certain disease or health risk that we only had in our original data set white males. And then all of a sudden, the data set that we have later of new data coming in is a more diverse population. It's not just white men. And oh, by the way, it's also you have other genders coming in, and then that's obviously things are changing. You would expect it to change, and so the model really wouldn't be fair to other population groups if we're just saying, okay, here's my model, and this is what I'm going to use, and I'm not going to retrain it. It would be unfair to do that because it was only trained on white males, and you might find that it doesn't predict very well than anything outside of the arena of white males. Now, it might be okay to a certain point, but you might find that on certain types of diseases or health risks that you're looking at, that it just doesn't cut it for other populations groups. So that again is a model limitation situation where you got to go back and retrain it with a larger group, a larger population. And there's all kinds of other biases that we could run into in the world of predictive modeling. We have here something called systemic bias, where that you have, it's very similar to what I talked about before. You have specific groups that are persistently over or underrepresented. We have selection bias, where that the study is again it's not representative of the population of interest. And you have reporting bias, where that maybe you're doing only your research only in certain articles that are in your native language, or maybe they're only you're only looking at publications and topics that have positive outcomes and not the ones that have negative outcomes. So there's all kinds of biases that we could go on and talk about, that could really come back and hurt your model. And a lot of these biases are not intentional. Some of them are, they're unconscious type of a tendency, where you might have, just in your mind, you might have a certain attitude or a bias yourself that you just say to yourself, I don't think that's going to make a difference in the predictive model, but in reality, it does. So all of these kind of things you need to worry about on your model limitations and things that you're doing on your model. And these are all things that can lead to low model performance and low levels of generalization to unseen data. So now what I do is I hand it back over to Bob, who's going to talk about some imbalanced data sets. So Bob, you can take it away.
All right, thanks, David. I would mention that there are actually about 200 types of biases that have been described in the literature. Let's see. Are you seeing my screen?
Yes.
Okay. All right, we're going to go about 10 minutes longer only. So this section will be talking about the significance of imbalanced data sets. And then next month, we'll start on how do you solve that? How do you tackle imbalanced data sets? Think about how common that is in medicine. What you're looking at, those people, for instance, that are intubated in the ICU versus those people are not. If they're intubated, it's in a minority. The same is true of biopsies of, say, a breast biopsy. The minority are cancer, the majority are benign. So you've got to deal with that. It's very common, again, in medicine more than other fields. The second point is there's no formal definition of imbalance. You can read these definitions that range all over the place. And I would say to you that there's no perfect definition. Certainly, if you start to see evidence that sensitivity is lower than you would expect and specificity is higher, then you probably have an imbalanced data set. But it could be 5-to-1, could be 10-to-1. It's difficult to say. So you notice that each one defines it slightly different. But what you need to be aware of is it affects the model you created, particularly the classification model, and particularly accuracy in AUC. So one of the pretty well take-home points is if you do have class imbalance, you throw out accuracy. And the AUC is also suspect. We'll be going over those things that are much more reliable. Other point, take-home point, as you might say, well, I'll just go to a national or international guideline and look for advice of how to handle this. I got news for you. Tripod, which is one of the earliest, doesn't mention it. Other articles and guidelines also don't mention it. I think they stay clear of it for a good reason. Number one, it's hard to define. Number two, the best method is individualized of how you handle it. And we'll go over that. Our hope in the future for AI is it will look at the imbalanced data. It'll run 7 different solutions. It'll say, after considering all 7 solutions, we recommend the following for the following reasons. That's where we think it'll be, or you'll see it in the not too distant future at the rate things are changing within 1 or 2 years. Again, an important statement here is when it comes to predictive modeling, there's no free breakfast, lunch, or dinner. You have to do the hard work in terms of preparing the data and looking for data challenges and model challenges that we've already discussed. So let's see. Okay, so basically I've highlighted what we consider important. You will be splitting data into train and test, and you'll be using the data sampler widget. And in there is a box that you should check called stratified sample. And what that does, so you've got, say, 75% of your subjects are training data subjects, 25% are test. What you want, though, is you want to, so if you only have 20% cancer, you want the training data to be 20% cancer and the test data to be 20% cancer. So that's what that stratified sample means. And all you have to do is check the box, because you don't want all of the cancer patients to show up in training and none in test, or vice versa. So we'll start talking for a few minutes about the performance measures that work when you have class imbalance. And again, this one, I think we may need to go over twice. But basically, instead of looking at the receiver operator curve in this scenario of class imbalance, you look at precision and recall. Why? Because they deal with the minority class, or some people call it the positive class, or the class of interest. So that is the most relevant. The same would be true of the F1 score. It deals with precision and recall, and that's what you're most interested in. Refresh your memory, sensitivity to recall is true positives divided by true positives plus false negatives, because a false negative is actually positive. Precision is really one of the few good terms. How precise are your positives? It's also called positive predictive value. It's a ratio of the number of true positives divided by the sum of the true positives and false positives. And so it really is basically telling you how good your model predicts positives, true and false positives. Now, I think what I'm going to do, because we don't have many minutes remaining, I'm going to introduce you to something that's surprisingly helpful for whenever we're talking about the receiver operator curve or the area under the curve, the receiver operator curve, or the area under the precision recall curve. We're going to mention threshold, and this creates confusion. Most people do not understand that you can move the threshold. It's arbitrary. So I'm going to spend a minute going over this, and then next month we'll go over it again. It's that important. The two things that are so important in models that anybody should understand but are constantly confused is the receiver operator curve, and secondly, the confusion matrix. Probably that was aptly named, but shouldn't be. It should be easy for everybody to understand. So this came, by the way, for the machine learning university by Amazon did this. There's an option called Explain, which contains all the interactive charts. So this is an interactive receiver operator curve, but the same would apply to the precision recall curve. And let's try to explain it. The beauty of this is how it all started. The receiver operator curve dates back to World War II with super early radar, where the operators were trying to decide what's an airplane and what's a cloud. So you start with the threshold of 0.5. Anything to the right is considered an airplane, anything to the left is a cloud. Or in terms of like how logistic regression would look at it, they would consider everything to the right a 1 and everything to the left a 0. But notice when you use this default of 0.5, that sure, you pick up a fair number of airplanes, but look at the clouds you picked up. So like so much of modeling, these are false positives. These are false, the airplanes over here are false negatives, right? Well, what happens when you move this? But as I do this, look down below it. Look at all the data points. The way a receiver operator curve is created is that it looks at all these different thresholds, going down, going up, and for each threshold, it draws a new point. In other words, so let me get this a little closer to 0.5. Okay, so here's the threshold at 0.5. At 0.5, the true positive rate is 0.57. The false positive rate is 0.23. You can prove that by just going straight over. True positive rate is 0.57 over here. The false positive rate, if you drop it down here, is 0.23. So that's 1 point on the curve with a threshold of 0.5. But notice what happens if you shift the curve this way. Just let's make it 0.7. Now your true positive rate drops dramatically to 0.25, and your false positive rate drops dramatically also. So you got rid of the false positives, but at the price of the true positives. So notice you got mainly airplanes, or totally airplanes, no clouds, but look at all the red airplanes you missed. So this, I think, is the best demonstration I know of, but this is how a receiver operator curve and the area under the precision recall curve are created. And that's why the ROC curve should never be completely smooth. That's a Hollywood feature to make it look nice. It should be jagged because each one of these represents a different threshold. So I wanted to show that, but I think with that, we want to stop it, and I'm going to stop share and open up for questions. And we'll resume where I left off, talking more about the measures. How do you overcome that by using different measures? So are there questions before we close this session? Please keep in mind, this was video recorded and will be on our YouTube channel in a couple of hours. Questions? Don't be shy. I would ask point blank, though, whether you understand the idea of the threshold, because that's so important.
Thank you, Dr. White. I thoroughly enjoyed this session, but I think I might have to go over the previous lectures first to kind of like bring it all together. But I did understand today's session, like all the area under the curve and the RC.
Okay, we'll take up where we left off, but I think there'll probably be one or two new people and so forth. We'll start with going over that interactive chart. I think that's much better than a PowerPoint or any static way of representing it. But if there are no other comments, questions, or concerns, we'll go ahead and stop this session and hope to see you next month in September.
Perfect, thank you. I do have a question about the certifications that you mentioned that you're trying to bring. Are they different from the one that were discussed at the conference offered by the ABAIM?
Yes, totally different. Yeah. And again, we'll announce more about that, but you know, that is our goal, is to certify people in data science that does not require programming.
Right, that would be perfect. Thank you.
Okay.
Dr. Hoyt, I have a question. So you mentioned about ML ops. So more analogous to healthcare system or health system settings. Suppose you develop a model based on the patient data, and you want to deploy it at the EMR level and everything. Do you have any like a process in the real world healthcare system settings?
There are not many good real world models. I mean, that's an important point. Very limited universities can actually use, and wouldn't it be nice to have live EHR data, not retrospective data? So I think you're going to see that. I hope it's demanded by physicians and everybody involved in biomedical data science, that we have more live models at different universities, because you know, it's conceivable that Mayo Clinic and Stanford will have different results, and certainly different than a non-academic medical center. So we need to be able to have the technology and the expertise to hook up the pipeline to get that done. So all too often it trains on retrospective data, and that's where it ends. It needs to be prospective data. It should be live data, and it should be studied, and that is what should be published. So, I mean, it's a very good question, but we definitely need that.
Thank you.
Okay. Any other questions or comments?
Do you have a sense of when the book will be publicly available to us in its entirety?
That's a question worth answering. We're in the process of the final edits. I think, keep in mind the following: will be done probably by the end of this month, but to get a print book, it'll require a book designer, and that will require weeks and weeks. So that being said, I don't think realistically probably before October.
Okay, thank you.
Dr. Hoyt, I noticed some typos or something in the material you sent. Do I just send you like where I noticed it, because you'll be publishing it in future?
Feel free to, but keep in mind, we have not gone over the chapter yet like we are now. In other words, we realize there are a few typos and formatting. The formatting has been good, but not great in Google Documents. The left margin, for instance, we can't set it reliably. But
Sure.
yeah, feel free to do that, but we're aware that there's some, but we again, we'll be going over chapter 4 and 5 soon.
Okay, great, thank you.
Okay, any other comments? If not, have a great weekend. Hope to see you in a month.
Hey, everybody, take care.
Thank you.
Bye-bye.
Bye.
Bye now.